Okay, let's get started. So, oh, yeah, that's our fearless leader. There we go. All right, so did you all find the welcome video okay? Everybody online find the welcome video. So that went through the details of the syllabus and the logistics for how we're going to conduct the class. So I'll just run through a couple things on that right now before we get started so we're on the same page. So as you can see, we'll be using Zoom. I have 3 students currently in class with me, which is great. There's plenty of room for more. We're in an auditorium. So as many as want to attend in person, there's plenty of room for you. Obviously, I can see most of you are attending synchronously, so online. And I'm also, of course, recording these Zoom lectures as well. And those will be put up on YouTube with the link in Blackboard, usually right after class or very soon after class. So let me just run through a couple things to make sure there's no questions. So I talked a little bit about textbooks in the welcome video. Is any questions on textbooks? Oh, sorry, let me actually start with Zoom etiquette because it's relevant right now. So for small classes, when most of the students are on Zoom, it's easy to raise your hand, either actual hand or your virtual hand, or just call out and try to get my attention. For a medium-sized class like this, it'll be better if we use the chat. So typically what will happen is I'll be lecturing happily along. I will periodically look in the chat to see if there's any questions. You can chat to each other, you can chat questions, or you can just say, Professor Kessel, I have a question, and then I'll call on you. Or there's now a raise your hand function, but I won't necessarily call on you right away. We'll wait till there's a natural break in the lecture to call on you normally. But for now, just go ahead and blurt things out, unmute yourself and blurt things out if necessary. So are we okay on textbooks? So there's no required textbook. I have a book coming out soon-ish. It's not out quite yet, which covers pretty much everything that'll be covered in this class, plus a lot more. And there's also a book in the syllabus that I suggested if you would like a more typical undergraduate level numerical methods book for engineers, then Galat and Subramaniam is fine. And also, as you've seen, I've provided you with the lecture notes, so which we'll talk about in a second. So you don't need a book at all, but if you'd like one, then there's pros and cons to both of those options. In terms of prerequisites, basically, I laid that out by topic. So by course, there's pre and co-requisites, lots of them, but I laid it out by topic. So in other words, what you'll be carrying forward from Math 251 and 252 into this class, CS 104, basically a little bit of a background in programming, not much as expected, but a little bit. So if you have any questions about your situation personally, just email me or talk sometime and we'll get that sorted out. Most of you have been taking advantage of the Slack invite. I imagine many of you have already used Slack to some extent in other classes. The key to Slack is you guys, so the way we'll use Slack in this class is I will monitor it, but I'm not going to necessarily be the driver of it. So I will monitor it, make sure that we don't get off on silly tangents and you're giving each other wrong answers or suggestions to the questions that you're raising. But I'm not going to necessarily be driving the Slack discussion. Maybe I'll post some things periodically, but for the most part, this is for you guys to communicate with each other. You're not all in the same room anymore. So especially for a class like this, especially for a class that involves use of computers and software, you'll often just have little questions. I'm using Python, and when I put this value in for this parameter, it gives me this silly result. What's going on? And to move on, you just need to get that simple question answered. So it's an opportunity for you guys to help each other out, but it depends on you. So it could be a very vibrant source of discussion and platform to discussion, or it could be completely dead in a matter of a week and everyone ignores it. So the good news is most of you have been accepting the invitation, so that's obviously a start. Then the next step is to be active. So check frequently, you know, turn notifications on your phone or your computer, your tablet, whatever you use regularly, and look at the questions, respond to the questions, start and continue and contribute to discussions along the way. And that will make it work for all of you for the best. In terms of the lecture notes, you'll see them in a second, but you saw them. They're on Blackboard. So it's just a giant PDF file for the entire semester. And I will obviously be projecting those slides, but it's not just a bunch of PowerPoints day after day, class after class. So you should have some mechanism for either annotating directly on the slides, writing on the slides, or something. And I will say that nowadays, there really is no good substitute for a good tablet and electronic stylus. I use an iPad and Apple Pencil, but Surface or something works just as well. Obviously, you can go old school and print out the slides and write on them, or you can take notes in a more traditional fashion and then kind of somehow merge them with the slides. But try to develop something that works well for you. But the way they're kind of designed is that you have the slides in front of you in some form, electronically or physically, and then you're able to scribble on them. So a lot of times I'll do examples, but I'll write out the examples by hand, but directly on the slides, so that it's all in one place. You don't have, one set of, my set of notes, then you have handwritten stuff someplace else, and then so you can do it all in the same place. So the nice thing about it, and this is kind of and this is pre-COVID, this is not because of COVID, although it's been helpful in light of where we're at right now. But there are just certain things that are best presented in certain ways. So today I'm going to introduce you to computational mechanics. And I can cover a lot more, and I can show you some pretty pictures, and we can see some interesting things if I primarily do that as prepared slides that I show you and you have available to you. But then other things, like maybe some derivations or examples, sometimes a figure, it's better if I walk you through it. And so I draw the figure, talk you through it, we do the example, rewrite it out by hand. But all of that you can do within this one PDF file. So sometimes you'll see blank spaces or pages. That's stuff that we'll be filling in during class. So that's the idea. Everyone has different ideas about writing versus PowerPoint versus everything else, all the other options. In my mind, this gives me the maximum flexibility, not even on a topic by topic basis, but on a slide by slide basis. What's the best thing? What's the best way to get this across to you? And so that's my thought process, and hopefully you'll find that helpful. So those are available on Blackboard. The notes is a big PDF file. All right, are there any other questions before I get rolling? We'll discuss programming languages a little bit today and more as we go. So we don't have to get into great depth yet of MATLAB versus Python versus whatever. So we'll kind of ease our way into that. But any other questions about logistics or syllabus stuff? Anybody online? Okay, so let's get started. So here we are, and oops. So computational mechanics. So I'll discuss the name in a moment. It's a bit of an unusual name. A lot of times you'll see, if you look in other programs, they just call it numerical methods or numerical methods for engineers or something like that. There's actually a reason why we named it this, and I'll discuss that in a little bit. But let me just first introduce the topic. So this is going to be a very different course than your other courses in a number of different ways. Hopefully you'll find it interesting and kind of fun, even, if I could put it in those terms. So let me introduce kind of where we're going with this and what this is all about. So Introduction to Computational Mechanics. Let me get my LaTeX off of the side there. It's a little bit distracting, isn't it? We'll just put a nice picture of IT in the background. There we go. All right, so Introduction to Numerical Methods. So I said this is not, strictly speaking, Numerical Methods class, but let's start there. Let's start the discussion with what are numerical methods, why do we use them, why do we need them as engineers? We all have maybe some fuzzy ideas of what that means, but let's just be very explicit. So if you go back, way back to your elementary school days, and you think about the math that's led up to today, the math that you've had leading up today, obviously it starts with arithmetic. And the reason why I even mention arithmetic is because when we do arithmetic on a computer, we actually have to be very careful about how we do that. And a number, we're used to 2/3 is 2/3, right? Well, 2/3 on a computer is actually not 2/3, it's something else. So we're gonna have to go back and kind of rethink how we do arithmetic, not how we do it, but how arithmetic is done in the context of a computer. So arithmetic, basically looking at numbers and operations between numbers. Then we had algebra and trig, and that was emphasizing functions. So we went from numbers to functions. Functions represent something, how something behaves in time, how something behaves in space. And then we learned how to manipulate them, represent them, and do all kinds of fun things with functions. Then we get to calculus. That's when things start to get a little more interesting. We focus on differentiation and integration of the functions that we learned about in algebra and trig. And then that segues into differential equations. So you should all have either had differential equations, Math 252, or you're taking it now. It is a co-requisite for this class. And that's where the math and the physics, the math and the engineering really come together and they merge together. And we can see finally why this math is so essential for us engineers. So that's kind of where we're at now, is differential equations. And the focus in all of these topics and all through the years of you learning math has been on obtaining exact, or we call them closed form solutions. So you have an algebraic expression and you want to solve for x. We call those roots. You have a differential equation and you want to solve for y as a function of x. So that's the solution of the differential equation. We have a function we want to integrate, so the area under the curve. We want a function, we want to determine how it changes with time or in space. So that's a derivative of the function with respect to t or x. But we're always learning how to do this exactly. So exact closed form. So the derivative of x squared is 2 times x. It's an exact expression. No approximations have been used at all. So again, in calculus, we do the differentiation, we do the integration, we get nice, smooth, continuous results. And that was the case in algebra, trig, all the way through. But as we quickly learn as engineers, that only gets us so far. So there are certain problems that can be solved that way. And we strategically choose the problems that we can solve in closed form or get exact solutions. But eventually we find out that most interesting and real problems in engineering do not fit neatly within this exact solution approach to solving these kinds of problems, whether it's differential equations, integrals, derivatives, algebraic equations, what have you. So the exact approach, the analytical approach, only takes us so far. We need to know it, we need to learn it, and we use it when we can, but there'll be many instances where that's not possible. So where those fail us, that's where numerical techniques come into play to pick up the slack. These are approximate. They do not give us exact solutions, so we have to sacrifice something. But what we gain is the ability to solve problems, whether it's differential equations, derivatives, integrals, algebraic functions, solve equations that we cannot solve exactly in closed form. But the sacrifice we make is that we're only going to get approximate solutions, not exact solutions. So this is numerical methods, or some people call it computational methods. We'll use the two words synonymously or interchangeably. So numerical methods are general ways to find solutions of algebraic, differential, and integral equations. However, that is now being done approximately. Now, modern numerical methods, the kinds of things that we'll be learning, they take the form of algorithms. So an algorithm is just a step-by-step procedure for accomplishing something. So in math, we have algorithms. Numerical methods, we're going to have algorithms, step-by-step processes for accomplishing some task. And they are typically being solved in digital computers. Now, the fact that we call them digital computers suggests there was actually something called an analog computer at some point in time. And in fact, there was. And so my favorite one actually is there was something called a Nordic bomb sight in World War II. So when bombers would fly their planes over the target, they would turn on the Nordic bomb sight, which would actually fly the plane in a nice steady fashion so that when they released the bombs, they would be more likely to hit the target. So this was an analog computer. Now it's kind of hard today to imagine what an analog computer even means. And we don't hear a lot about analog computers because they existed really only for a very short period of time before digital computers kind of took over the world. And everything we use now, including our phones and even watches nowadays, are digital computers. But these things were so valuable that if you got shot down, the bomber's job was to first destroy the Nordic bomb sight, even at the expense of your own life if necessary, because they were so advanced and thought to be so key to winning World War II, particularly in the Pacific theater, that they were valued very, very highly. Short period of time, analog, then digital came in. Digital just means lots of ones and zeros. Everything you do on a computer boils down to a string of ones and zeros. 1 is on, 0 is off. It's just a whole bunch of switches, ones and zeros. That's all it is, everything that you do. And it's done like in a clock fashion. So when you say the CPU is 3.5 gigahertz, that's the clock rate. That's the rate at which something can be done with a number, with a word, with an item on a computer chip. So all that to say, modern numerical methods are boiled down to algorithms, which are step-by-step processes to accomplish a task. And they're typically designed to be performed on digital computers, as I've just said. So therefore, there's also an intimate connection between the computing methods that are of interest to us as engineers and computer architectures. Now, normally we as engineers, we let computer architectures, that's for computer scientists and electrical engineers, right? We just buy them and we use them. But if we're going to develop algorithms that use their hardware that they develop, design, and build, then we're going to need to be conscious of those architectures insofar as they influence the computing methods that we'll be using. Now, what is a computer architecture? When we think architecture, you think of a building. A computer architecture is the overall structure or makeup of a computer. It's how the memory is linked, for example, to the CPUs. It's how many cores are in each CPU. How many CPUs do you have? How many GPUs do you have? And how do the GPUs access memory? So that's the architecture, the overall framework that defines the hardware itself. Now, so this takes us from the exact to the approximate and from continuous to discrete. So everything you've done so far, most of what you've done so far has been exact and continuous. So continuous functions, f is a function of x, it's nice and smooth. At any value of x, you know the value of f. So it's a continuous, smooth function. It's exact, the solutions are exact for the reasons that we've discussed already. Now they're going to be approximate. So we're not going to get exact solutions, we're going to get approximate solutions. We're going to get hopefully good estimates of the solutions, but they will not be exact. And they will be discrete. So it might be, for example, imagine that your f of x, or it could be f of t, say, it's some smooth curve, it's continuous, but say that is a function that represents the temperature as a function of, let's say, time. It could be time or space, but let's just say I put my probe, my temperature probe, I hold it in the same position, and I track as a function of time what's the temperature at that location. So I get f as a function of t continuously. If I could measure it continuously, I can plot it then as a function of time. In reality, those measurements are typically going to be at discrete times. There's some sampling rate that my hardware can measure the temperature. I can't measure it at an infinite number of times in some interval, only discrete. So every 14 milliseconds or microseconds or picoseconds or whatever. So that now creates a discrete chain. Basically, it's a list of temperatures at known intervals in time. So what that means then is, rather than the measurement of temperature versus time being a continuous function f of x, it's now a discrete set of numbers, which we can think of as a vector. So a vector, right, is just a list of numbers. Now, it might be a long list of numbers, but it's still just a list of numbers. So our continuous functions become discrete vectors. Okay, so that's a different set of mathematics. That's now linear algebra. So we're going to be using a lot of linear algebra, and we'll spend some time in chapter 2 reviewing it. And matrices will come in, vectors will come in, and they'll be very important. So the way the functions are expressed will not be continuous, but discrete. And the numbers themselves are no longer exact, they're approximate. So both of those things are going to have consequences for us as we move through this. So if we take these ideas and concepts into the discrete and approximate world of numerical methods, this requires us to have some understanding of how functions can be represented as series of numbers, again, as discrete vectors. How these numbers are represented on computers, they're not exact. Even 0 is not 0 on a computer. 1 is not 1 on a computer. It's only 1 to what we call machine precision, which is not infinite precision. So we're going to have to take that into account in terms of how we use our computers to do these operations. And so we're going to need to be able to manipulate vectors and matrices ad nauseum all the time. Now, more than simply developing approximate analogs to familiar continuous functions, in other words, we could just make this really simple and say, well, let's start back from first grade. I don't know, what did we learn math-wise in first grade? I don't remember, it was a long time ago for me. And then just kind of walk through the years. And let's say, okay, whatever we did in the math class, let's now learn how to do it on a computer. Well, that'd be pretty boring, first of all, and not terribly useful. So what we're going to do instead is to, in a sense, do that, but in the context of, all right, I want to solve some real engineering problems. But I don't want to just limit myself to solving problems for which I can get exact solutions in closed form, in the form of continuous functions. I want to be able to solve any problem my boss throws at me, which might be approximate and it might be discrete. So we want to expand the range of possible problems that we can solve and address using these numerical methods. So again, we have our temperature versus time measurements at a sequence of times. What do we do with that? How do we measure errors? How do we, if I have measurements of time and I want to convert that into a heat flux, how do I do that? What operations do I do to do that? Chapter 4 will discuss curve fitting and interpolation methods, and that will turn our discrete functions, which is a set of discrete data, into approximate continuous functions. That's curve fitting. And that allows us to do interpolation in between. So if I measured location, the temperature here and here, here and here, but I really want it here, how do I get it here from those 4 values? So that's interpolation. And of course, we want a computer to do that. We don't want to have to do that by hand. So the story really then starts with how we represent approximations of numbers and functions, but that's certainly not at all where it ends. So let me think about it this way. Let's help us think about it this way. So we have math, right? We talked about what? Arithmetic. And then we had algebra and trig. Then we had calculus and differential equations. Okay, so we've learned a lot of math. And then as engineers, of course, we want to solve real problems. So the bridge from the math to solving real problems is science. So that's why we learn science. So the science gives us the governing equations. And for the most part, that's what we're doing in most of your classes. So you go to 202, right? And you derive the governing equations for static equilibrium of thingamajigs. And you go to 313, fluid mechanics, and you derive the governing equations for how fluids move. And then you go to 323 and you learn how heat conducts and convects and radiates. And then you go to, where else can you go? Then you go to dynamics class and you learn about equations of motion, F equals ma, and how you apply that to systems and get governing equations. So the goal in all of those is to get the governing equations, which are mathematical models of the physics. So the math, along with the science, leads to our governing equations, our mathematical models of physics, of our engineering systems. So that's what we've been spending most of our time doing. And then every once in a while, in reality, it's actually not very often, but we only show you these, so it seems like a lot. Every once in a while, we're able to get an exact solution of our mathematical model. And then we're happy, and then we move on. But in reality, and in most real engineering problems, that's not the whole story. We also have to look at, to get to real engineering research and practice, which of course is where we want to be as engineers. In order to get there, we need another bridge. That bridge is this class. So it's numerical methods. All right. So it's really the three things together. It's the math, which we've been learning all of our academic lives, along with the science that leads to our governing equations, or mathematical models of reality, such as Newton's second law, F equals ma. That's a model. That's not really a law. We call it Newton's second law, but it's not really a law because it doesn't always work. It doesn't work for, at quantum scales. It doesn't work at astrophysical scales or very large velocities. So it's a model. It works pretty well, but it's a mathematical model. And then we solve it exactly when we can. When we can't, then we use numerical methods, which is predominantly what we're doing in research and practice in engineering. Okay, we'll talk more about this in the context of what I call the numerical solution procedure. I'll define that explicitly. We'll walk through it later in the semester when it becomes necessary. But for now, this is a bit of a simplified version of that, where we have the math, the science, and the numerical methods coming together to allow us to do what we really want to do and solve real problems in engineering. Let me give you a short history. I know when I was your age, history, like, oh, roll your eyes to the back of your head, history is boring. This is going to be kind of an unconventional history. It's from an engineer's perspective. I'm not a historian, I'm an engineer. So I want to describe to you how numerical methods and the tools that we've been able to use, both hardware, software, and so forth, have kind of evolved to where we are today. And the reason why I like to do this is because, personally, I think it's fascinating. But secondly, it gives us a perspective of where we've come from and where we're at, because this is changing and evolving so much. And so throughout your careers, this is going to evolve and change tremendously. So you can sort of figure out my age, and you can kind of figure out where I started in this whole continuum of historical events, and so what I've experienced and where we are today. I'll keep it short. We're not going to get into a lot of detail, but again, it's going to be from an engineer's perspective, not a, the transistor was invented in by so-and-so, blah, blah, blah. I could care less. All right. So we're looking at the numerical computational approach to research and practice in both science and engineering. These are really both, this is kind of a weird thing to say, but this is both an old and a very new thing. So it's old in the sense that some of the first approximate methods were developed by people like Leonhard Euler. Leonhard Euler was one of the inventors of calculus in the 1600s. So this obviously goes back hundreds of years. And he has a method for solving differential equations that we still use today called the Euler method. And so these approximate methods go way back, predating way before digital computers. Things like estimating values of pi, right? So pi, 3.14159, blah, 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 and it goes on forever. It's an irrational number, so there's an infinite number of digits of pi. So a fun exercise that mathematicians have done for many, many years, in fact, centuries, is to challenge each other to calculate more digits of pi. Now, it's just kind of a fun thing to do. You go to a party and it's boring, so you all go back, find a computer, and you start calculating digits of pi because there's nothing else, no interesting conversations going on in the regular party. So there's even a method, it's my favorite method. It's called the method of exhaustion. So you literally, so pi, right? It's related to the circumference and area of a circle. So you take your circle, and if you divide it up into triangles, like pieces of a pizza, or pi for pi, get it? So you take your little pieces and you calculate the area of each little triangle. Now, if it's a triangle, it's not quite right because the circle is curved and your triangle, of course, is straight. But the more slices you take, the closer and closer and closer it gets to the area of the circle. The smaller the difference between the curved and the straight edges of the polygon versus the circle. So the method of exhaustion is literally, well, I can do more slices of the pie than you can to get into digits of pi. And it's just tedious calculation after tedious calculation, but that's what it's called, method of exhaustion, because, well, it was exhausting. People still do that, so not that way, but you develop a new computer, and oftentimes one of the new things you do on that computer is challenge the computer to calculate the digits of pi. So how many millions of digits can I get in a reasonable period of time? And then you can say, well, my computer's better than yours because it calculates pi faster. Woo-hoo. All right, so the point is, we've been thinking about these approximate methods for many, many years. But it wasn't until the advent of the digital computer in the 1940s and 50s, so we're talking, half a century ago, a little bit more now, when digital computers came in and became usable, and that just revolutionized everything. Because now all those tedious calculations required to calculate pi, solve a differential equation, you can now have a computer do rather than doing it by hand or using an abacus or counting on your fingers and toes or some other such thing. So we moved from hand executed devices, which I'll talk about, to electronic devices. And of course, that's what we're still using today. And the computers get faster, they get smaller, they get less expensive, but more powerful. But it all started with hand executed devices. So we'll start the story there, starting all the way back with pencil and paper, and then abacus and slide rule. The point here is, so now we're unshackled. So we don't have to think about and actually do all these hideous calculations by hand. We don't have to calculate the areas of little triangles over and over again, thousands or tens of thousands of times to estimate pi. We can have the computer do all the boring bits, and we just sit around and rejoin the party and wait for the computer to finish. So that's what computers love. Computers love doing the things we hate. They love doing the boring things that we hate. So there's been a tremendous rate of development in both the computing hardware as well as the algorithms that we use to do the calculations. So even in your lifetime, obviously you've seen how much faster computers have gotten. Everything now is multi-core. My watch, I think, has 4 cores, which I don't know what it's doing with all 4 of those cores right now. I guess tracking my pulse and my, I don't know, who knows what. Your phone has multiple cores. So multiple cores means multiple logical processing units that can be used to do something, in our case, some sort of calculation. So we have parallel computers in our pockets and on our wrists and in our backpacks. We carry under our arms today. So it's amazing the hardware that we now have available to us, and it just keeps getting better and better and faster and faster. So that's something that we can continuously take advantage of and look forward to. So as we develop more algorithms and software, okay, so that's one ingredient. That's the focus of this class. So our class will be focusing on numerical methods, how we use those to solve physical problems. So that's the software, that's the algorithms. That's going to be the focus of this class. But you layer that on top of the hardware developments that the computer scientists and electrical engineers and computer engineers are focused on. And that gives you, us, the engineer, where we want to solve physical, chemical, biological systems, an amazing array of tools. So a simple way to think about this, the reality is much more complicated than the way I'm going to draw this. But if you look at time, and time here is in terms of years or decades, and some measure of speed. Okay, so the speed of the computer, how long I have to wait to get the solution to something. The hardware keeps getting faster over time. Now, again, it's not a straight line, it's a squiggly line with some jumps and dips and doodles here and there. But over time, on average, it just keeps getting faster and faster and faster. So I can take a code I wrote when I was a junior in college, like you guys, roughly speaking, or sophomore in college, same exact code. I could run it on a computer today, and it will run many, many times faster, simply because I'm running it on better hardware, faster hardware. So that's great, but of course, that's not enough. So we're not just sitting around, running old 30-year-old codes on modern computers. So layered on top of that, we have the algorithms and the software as well. So that becomes another source of increased speed. So we're developing better algorithms, better techniques for solving problems, and we're running them on better, bigger, faster computers. And so the net result is, over time, we can either do much bigger problems, or we can do the same problems to get the answers much faster. So that's a win-win for us as engineers. This is great. So that's why there's been so much and just tremendous growth and progress in numerical methods, scientific computing, in engineering and science. And this is not an overstatement at all, but much of what we know today, scientifically and from an engineering point of view, would not be possible if it wasn't for this digital revolution. And again, I mean both of these, not just the hardware improvements, but the software and algorithm improvements as well. So this is for someone else to worry about, we just take advantage of, but this is our focus, coming up with the better algorithms to take advantage of the new hardware. All right, so basically in my little history lesson, it's just a few slides, we've always had essentially 2 form factors. A form factor is like a laptop computer. That's a form factor. So since I think the first laptops that I recall came in the 1980s, they were kind of big and chunky, but obviously it's something you can carry with you and use on the bus or on the train, or I was going to say your car, but not while you're driving, obviously. So we've always had something that sticks on, as engineers, on our desk, and something that we can hold in our hands. So let's start with the handheld devices first. It actually started with math tables, not this kind of table, but this kind of table. That kind of table. Number after number after number. So this started back in the 1600s, continued up into about the 1960s, for several centuries. If you wanted to know the log of a number, you didn't have an electronic calculator to compute it. You didn't have Wolfram Alpha to get it. You didn't have your smartphone with a cute little calculator on it. So it was all tabulated in a book to some number of significant digits. So you carry around, this was a handheld device. You carried around, this is my Abramowitz and Stegen. This marked the end of this era. It was actually published in 1964. This was kind of the last big hurrah of these tables. And it's just page after page after page of tables of all kinds of crazy functions and operations on various things. Very tedious to use, and obviously not a lot of fun to have to carry around. But that's what we had. Then came the slide rule. If you have a parent or grandparent that was an engineer or scientist, they probably have a slide rule, or else they had one. I actually have my dad's. This is my dad's slide rule. So these started, actually the history goes back before 1930, but from an engineer's point of view, this lasted for about 40 some years, 30s through the 1970s. And this is great. It's got a nice little hook. I can hook this on my belt. Very stylish. Walk around campus with your slide rule. They called them a slip stick. And that's all it is. Just like it looks there. They're always yellow for some reason. You got a nice little slider and a cursor, and you can do logs to about 3 significant figures. Why would you want to do that? Well, you can get all kinds you can get exponentials from logs, right? So if I want to really do an exponential, I can do that from a log. So you have a whole class on it's two-sided, a whole class to learn how to use this to calculate stuff. Well, why is this better than this? Well, obviously this is a whole lot smaller. It's actually less accurate because, like I said, it's only 3 or so digits of accuracy, whereas here usually you had 8 or so digits of accuracy, but it's a lot more convenient. And when you got good at it, you could get really fast doing I mean, not really fast compared to a modern computer, but really fast compared to doing this by hand. So this, okay, so 40 years, that's not a long time in the long history of computing devices, but for some of our predecessors, that's what they used for their whole career, or good portions of their career. So for my dad, he used this for the early parts of his career, and then of course, switched over to digital computers later on. 1970s is when the pocket calculator came in. TI, it still exists today, obviously. Many of you have TI calculators. This is a TI-30, which was a famous calculator for many, many years. You can see there pi to 1, 2, 3, 4, 5, 6, 7, 8 digits. This was amazing. Look at this. We've got square roots, we've got squareds, we have reciprocals, we have sine, cosine, and tangent. We have pi, all in this little device. It was about this big. So it was kind of chunky, it's a little bit thick, but compared to carrying around a slide rule, this was a huge advance. Now, these things were very expensive. The first ones, the early ones, were a couple $1,000s. Thankfully, they went down in price very, very quickly, and the functions that they could do increased dramatically. But this was an amazing advance. So again, think about it being a day-to-day engineer. You need something you can carry with you wherever you go and do quick calculations by hand. I didn't add it formally here, but nowadays we'd also, of course, add the smartphone. So some of us still like our calculators, but some of us have replaced our calculators with smartphones. And I put 2007. Why? What happened in 2007 with smartphones?
iPhone came out.
Exactly. The iPhone came out. So that marks the beginning. Anything happened before is irrelevant. You can't see my wry smile under my mask. Yeah. So now, of course, the smartphone. Huh? Oh, okay. So the smartphone, to some extent, has replaced the pocket, not replaced, but augmented the pocket calculator. Some people love their calculators. It's kind of like your childhood blanket. You know, you carry with you wherever you go. You bring it to exams, even when you know you're not going to need a calculator, because it's just comforting to have with you, and it fits in your pocket and makes you look smart. So the point is, that's handheld devices. We've always had a handheld device, something we could carry with us, portable, take with us to meetings, go to someone else's office, do some quick calculations, and so forth. Then we've also always had something that stood on our desk. And so today, of course, that's typically a laptop, could be a desktop, but more often than not today, it's a laptop. Maybe it's an iPad or some other tablet device. But there's a long history of these as well, not going back as far. So we'll start with digital computers in the 1940s when they first came in. This is a picture of a Cray 1. So Crays were supercomputers of the 60s, 70s, and 80s. These were fun. So they've taken off some of these panels here so you can see inside. The CPUs are actually in the top here. And then all the cooling equipment is down here. These are actually seats, so they're nice padded seats. So you work all morning, and then you sit here and you have lunch. And the computer does all the work. These things generated so much heat in the 1990s. There was a Cray YMP, so a version of these. It costed on the order of $30 million, very expensive computer. By today's standard, it was very pedestrian, very slow, but in those days was very, very fast. And they had it located actually in the basement of a Westinghouse research center outside of Pittsburgh. They used the computer that looked very much like this. They kept the same form factor to actually heat the building. This generated so much heat, they would extract out the heat, ducted it into the building, and that's how they heated the building in the winter. Early on, these were generally remotely accessed. You could not afford to have one of these on your desk, quote unquote. So you had some other, usually they call them a dummy terminal or something on your desk that was connected to the mainframe or to the servers. Now, of course, we think in terms of the cloud, which is just a big network. But anyway, the point was that we were generally remotely accessing a computer someplace else. It might be in the same room, might be in the same building, might be in a different building on the same campus, or it might be somewhere completely different. But that's the computer that we were interfacing with and accessing. Then came computers for individual use. This started really in about the 1970s and still is going on today. We used to call them workstations. So a workstation was basically a big computer. So the personal computers of the day were smaller and less powerful. Workstations were bigger and more powerful. If you're a Jurassic Park fan, then you may recognize this computer. So I don't remember if it was Jurassic Park 1 or 2. If I had to guess, I'd say it's 1, but I don't remember. If there's any Jurassic Park nerds, then you may remember there are scenes in the movie where you see a row of computers. They were this computer. Now you say, well, why this computer? This is an SGI or Silicon Graphics computer. And the reason was because these were the computers that were used to do the CGI for the dinosaurs and for the movies. And that was back in the 90s, early days of CGI for movies. But we used them in scientific computing. I had one of these when I first came to IT. This is an Indigo 2, and there's different versions of this. But anyway, the point is, this is a standalone computer. So this is now a complete computer on my desk. These cost on the order of $15,000 to $20,000 each. So they weren't a personal computer, they were a workstation. They're more powerful, faster, more memory, and so forth, had more technology in them, but they were still something you could stick on your desk and use. So now you're directly accessing that computer, and that's the way things have been since then. So we all have our own computers, and then we're communicating with each other through the network rather than the computer being centrally located and all of us remotely accessing that one computer with our dumb devices that don't have any CPUs in them. Some important developments. Again, I'm not going to get into super nitty-gritty history stuff here. If you have probably a grandparent more than a parent, if you have a grandparent who is into fixing old TVs or had some old radios or something in the garage or the attic, ask to look at the back if it's from the 1950s. What you'll see are what are called vacuum tubes. They look like small light bulbs. They're usually kind of skinny and tall. Sometimes they're skinny and short, but they look kind of like light bulbs. Each one of those was an on-off switch. So obviously you can only have a handful of them behind your TV because they were kind of big. The reason why I bring that up, because the big hardware innovation was the transistor in the form of integrated circuits. That came along in the 1960s. Does anybody know where transistors were first developed? What company developed them? Good old AT&T. So AT&T Bell Labs, which for many, many years was a premier world-class research organization in New Jersey. Bell Labs still exists, but it's a small, mere shadow of its former self. They invented lasers, they invented the integrated circuit, and you'll see them mentioned again in a moment. This was a huge innovation because these integrated circuits, each one of those vacuum tubes, which I could hold, one in each hand, that's one switch. Now, with an integrated circuit, you could have a whole bunch of transistors, thousands, millions, billions, trillions, huge numbers of transistors on one little chip. So a typical CPU now has just unbelievable numbers of on-off switches on it, transistors. That's an integrated circuit. So we're still using that, basically the same technology. Now, if you follow the industry, you'll hear about, so-and-so can now manufacture 5 nanometer, and then now they're moving towards 3 nanometers. So every time they get smaller, the manufacturing processes get more difficult, but because they're smaller, you can pack more transistors on the same chip, and so it gets faster because you have more on and off switches. For engineers and for scientific computing, the onset or development of Fortran was hugely instrumental in advancing our ability to use computers, digital computers. It started in 1954. Fortran stands for Formula Translation. It was a high-level programming language, and high level just means you can read it. You can look at a Fortran code even if you don't know Fortran, and it will make sense to you. Maybe you can't write it, but by reading it, it'll make sense to you. It's in some form of English. It started in 1954, and I'll show you in a moment what programming looked like before this. So this high-level programming language, along with its focus on numerical computing, not computing for the sake of computing, to make an app for your phone, but for the singular purpose of doing numerical calculations. That's what Fortran started as and what it still does today. It's still around. People kind of poo-poo Fortran, it's so old and decrepit. Fortran has evolved over the decades and aged very, very well. And what they do is they remain singularly focused on us, on numerical programming. They don't give us all the bells and whistles that you have in C++. They only pull in the ones over the years that make sense for numerical programming. So in fact, Fortran codes are still the fastest codes. So if you take an algorithm that we learn in this class and you learn the step-by-step processes, you could program it in Fortran, you could program it in C++, you could program it in Matlab, you can program it in Python. The fastest one will be Fortran still today, because it has been designed from the very beginning to do one thing really, really well. C++, when they developed C++, they did not have engineers and scientists in mind. So Fortran still exists. We'll talk more about programming languages later. This one is not normally included in histories of computing, but I think it's tremendously monumental, and that is the development of Unix. Unix was also developed at AT&T Bell Labs. The problem they were having in the late 60s was that the computers were very finicky. So they'd be happily programming along, and they'd make a mistake in the program, and it would bring the whole computer to a crashing halt. And everything that everyone was doing on that computer was dead. You have to restart the computer. Everyone had to restart their codes again, just because someone made a boo-boo. So they wanted to develop an operating system, and that's what Unix is. They wanted to develop an operating system that was robust. So it turned out they did such an amazing job that now almost every electronic device actually has Unix on it. Raspberry Pis have a version of Unix on them. My watch is based on Mac OS or iOS, which is Unix. At its core, it's Unix. My watch has a Unix operating system on it. The only electronic devices today that don't use some form of Unix are Windows machines, Windows computers, Windows tablets, Windows anything. So tablets, phones, computers that are based on Mac OS or Android. Android is a variant of Unix. Unix has literally taken over the world. It started as a little pet project of a couple engineers at AT&T Bell Labs in the late 1960s, and is now ballooned to become by far, the best operating system in the world. Why? Because it's very robust. If one application crashes, the rest of the system doesn't come crashing to a halt. Sound familiar to you Windows users? All right, so Unix was a huge development and turning point in this, almost everything. You look at clusters, large supercomputing clusters with tens of thousands, sometimes even millions of CPUs that take up whole rooms in computer facilities. They're all based on some form of Unix, like Linux is Unix. The other big development was networking. Now, networking started in the 1960s. Obviously, it looks very different today than it did then. Now we have the internet, which is our primary form of networking. So there's LANs, which are local area networks. So that's basically a computer network within a building. And then there's campus-wide networks, but then the internet, of course, is global. So that has always played a role in scientific computing. So you see there's a mix of hardware and software. Software. Both of which have had tremendous impacts on the development of computing. Now, programming styles, the way we actually program a computer, the way we actually tell a computer what to do and how to do it, has also evolved tremendously over the years. This is a picture of the ENIAC. This was not the first digital computer, but it was one of the first that was actually useful. It was actually used for doing projectile trajectories. So here's a picture of it. And it was actually first developed in 1945. So this is the latter half of the 1940s. You can see lots of wires here. I just found this picture recently. This is amazing. This is one 8.5 by 11 sheet of paper. This device right here, that is not one gigabyte of RAM. It's not 1 megabyte of RAM. It's not 1 kilobyte of RAM. It is 1 byte. 1 single byte of RAM was, it's like this high. It's crazy. My point is, how was this programmed? This was manually programmed. If I want to program it to do something, so I want to check my Twitter feed, right? So someone had to come in and they had to rearrange how these wires were all attached. Boop, 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 boop. Unplug this, plug this, unplug this, unplug that. And then after a couple hours of that, I can check Twitter. Now I want to check Facebook, right? Boop, 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 boop. Unplug this, plug this in, unplug this. Twitter and Facebook did not exist in the 1940s. Just to be clear, I know that. Don't report me to the historians. But anyway, the point is, each program had to be manually, each application had to be manually programmed. Then you could only run that one program until you were done. And then you would spend a couple hours, days maybe, and you would reprogram it to do something else. You know how we say there's a bug in my code? Do you know why we say there's a bug in my code? Think about it. It actually doesn't make any sense. There's a bug? Like what do you mean, an insect? There's not an insect in my code. It comes from this era. Notice this is 1940s. So these are all vacuum tubes. Behind this wall is a whole bunch of vacuum tubes. These are vacuum tubes right here. So what happens when a bug, say a moth, comes flying into the room, lands on one of these, and happens to touch the adjacent one, and it shorts out the vacuum tube? So that's where the term, I have a bug in my code, came from, because there was a literal insect that short-circuited something in the computer, and you got the wrong answer because one of your ones switched to a 0, and that messed everything up. There was a literal bug in your code, so we still use that term today. It's great. Punch cards. I am so thankful I was born after, or not born, but I was born into the computing world after the punch card era. So I brought some, I brought some punch cards. I love them because they make excellent bookmarks. They're a nice size and they're, not too stiff, but they got a nice little stiffness to them. They're excellent bookmarks. Each one of these cards is one line of code. So you can see in the picture there, it's a punch card. It punched out all these holes, and the pattern that it makes corresponds to one line of code. I can't read this one, it's too faint. That one doesn't have any. Okay, here we go. Here's this one card. Oh, that didn't work. It's a format statement. So that pattern of punches in that card corresponds to a format statement. So it's telling the computer, the program, how to output a number, how many digits you want, and so on. So each card was one line of code. So if you have several lines of code, several thousand lines of code, you have a stack of several thousand of these punch cards. So it's kind of cruel, but what would you do? Well, you don't have a punch card reader and a computer in your office, so you have to walk across campus with your stack of punch cards, and everyone laughs at you. There goes the geek, there goes the engineer, there goes the physicist. And of course, if they are really cruel, not cool, but very cruel, they would trip you, and you would drop all of your punch cards all over the floor, the ground. And then guess what? You had to put them in order. You can't change the order of your lines of code. You have to get them all back into the exact same order they were. And then you feed it into the reader. So it was a horrible era, horrible. And thankfully I came just at the end of that era. But look at these are awesome. They have IT on them, nice corporate logo, campus logo. And yeah, Anyway, so that was that lasted for about 20 years. And then we finally got to where we are today, which is keyboard entry. Now, I'm still waiting for it. I'm looking forward to someday when my grandchildren are sitting on my knee and they say, Grandpa, tell me again, what was that thing that you had to put your fingers on to communicate with the computer, to tell the computer what to do? Because at that time, they'll just think, do this, check Twitter, and boom, it'll check Twitter. What was that thing called? It was a keyboard. Oh, that's right. Can you show me your old keyboard? So that's where we're at today, keyboard entry. Programming languages. Okay, so this is 3 examples of 3 very simple codes. They all do the same thing. They print the letter A 1,000 times. Pretty boring. The first one is what's called a low-level language. So this is the way the computer speaks. This is closer to how the computer actually speaks. And you can see it's just a trail of numbers. And there's no way that you could remember that this trail of numbers is the correct trail of numbers to print the letter A 1,000 times. This was called machine or assembly code. So you basically had to write the code in the language that the computer speaks. Then we get to high-level languages, the first being Fortran, then came C, C++, now we have Python. So these are all high-level languages, which means they look like English. There's still a particular syntax to them. So there's a particular structure to the lines of code, and you have to put things in a certain order, in a certain way, but it's now readable. So there's a for statement. I is going to go from 1 up to 1,000. I++ means increment I by 1, and then do the stuff in squiggly brackets. And the stuff in squiggly brackets in this case is a print statement that prints the letter A. Fine, but the point is now I can read it. So you can just sit down, you can program this line by line. Matlab, this is what Matlab would look like, or Mathematica, to do the same thing. So it looks very similar to this C. This is C in this case. This is Matlab, so it looks quite similar. You don't have the open and closed squiggly brackets. Instead, you have just an end statement. You don't need the beginning one because it begins with the for statement. And you can see there's some differences in syntax. So I goes from 1 colon 1,000. So it's going to go from 1 to 1,000. And if you don't give an increment, it's going to default to 1. So 1, 2, 3, 4, up to 1,000. And then instead of print F, it's F print F. Okay. And instead of a double quotation mark, it's a single quotation mark. That's just syntax. So it's doing exactly the same thing. It looks very similar. It's readable, just a slightly different syntax, which just means the details of it look a little different. So these are very different styles of programming, particularly this one and these. All modern programming languages are obviously like this, not like this. Now, in terms of, and we'll finish up with this. So more specifically in terms of programming languages, there are many, many out there. There are dozens of them. If you go to, do we even have bookstores anymore? If you go to a bookstore and look for the programming aisle, you'll see dozens of different programming languages. Some are general purpose, some are more specific to certain types of programming or industries. But these are the 5 that have most impacted scientific computing or numerical computational methods. So they are in historical order of when they were introduced. So Fortran came first, then C++, Matlab, Mathematica, then Python. But they all actually still play a role today. So even Fortran is still quite modern. It has evolved tremendously over the years. It, again, still produces the most efficient code. So let me just go through these quickly, just to kind of give you an overview, and then we'll discuss them in more detail later on. So again, Fortran is specifically optimized for numerical programming, which is exactly what we're interested in doing. It produces the most efficient code, and yeah, it really is more modern than you think. So there's not a lot of people programming on a daily basis in Fortran, but there's a lot of Fortran code that is still being used. We call it legacy code. It's old code, but it's still often the fastest code for a given task. C++ then came along. This is more of a general purpose programming language. It is not specifically designed for us. It's not specifically designed for doing numerical programming, although you can. But almost all software today is actually written in C++, general purpose software. So it's very common. Most computer scientists know and use C++, maybe something else as well, but it's an important skill. But my favorite example as to why C++ was never designed for us is if you say, if you have a variable x, so you input in a variable x, and you want to take a power of x, say you want to take the 12th power of x, there is no way, there's no function built into C++ to do that. You have to write your own function to multiply x times x times x times x n times. This is an everyday, obviously an everyday operation we have to do all the time. And for whatever reason, C++ people never thought that anyone would ever want to do a power of some number. So C++ can be used for scientific computing, but it does not produce the fastest code, the most efficient code, and it's a bit cumbersome at times. Matlab and Mathematica, they're kind of competitors of one another. They're both commercial mathematical software packages. These are high level in the sense that you're writing in a English looking, like I just showed you, programming language. MATLAB actually stands for Matrix Laboratory, which tells you what it was originally intended to do when it was developed first in the 1970s. It was to do linear algebra. So it's really, really good at doing linear algebra operations. That was what it was originally designed for. Nowadays, it does a whole lot more, but that's what it was originally designed to do. The actual syntax in terms of how you enter in things and program it is quite similar to C. It looks very similar to C. It's been very popular in engineering contexts for a number of years. It's been around, like I said, since the 1970s. It's been updated, it's evolved tremendously over the decades, and it is still used in research, it's used in industry, so it is very popular in engineering. Mathematica has, in some ways, it's very similar to MATLAB, but it actually has a very different set of origins and history behind it. Originally, Mathematica was written to do symbolic mathematics. And what that means is, that's the math you would do on paper. So I want to integrate x squared. Well, so you work it out. Okay, so let's see, it's integration. So you increase, divide by n, plus 1, blah, blah, blah. And then I do this, check the limits. So Mathematica was written to do all that for you, symbolically, exactly. Which if you think about that, that is a pretty amazing feat of computer programming to be able to do symbolic mathematics like that. That's where it started in the 1980s. Again, it is like MATLAB, it has evolved significantly from there, and it now does a whole lot of other things. But that's Mathematica, high-level mathematical programming language. Then came Python. So Python started as a scripting language. Now, a script means the following. So say I work for JPL. Every morning I come into work, and I see all the downloaded images from some interplanetary probe, right? They all come in, they get stored on my computer, but they all have goofy names, the names that no one could decipher, you know, what planet it's looking at, what's the orientation, what's the location, what's the time. So every morning I have to change all the names of thousands of image files so that they are meaningful to my fellow engineers and astrophysicists and astronomers and everybody else. Well, I'm not going to do that one by one. I'm not going to change the first file's name manually, then the second file's name, then the third, and then the thousandth and first. And so you write a script. So a script is a short program, typically just a handful of lines of code that does something very simple. So you write a script that reads in the name, deciphers what it means, and then renames the file in a manner that is readable by my colleagues. So it just does something tedious. That's actually how Python started. It started as a scripting language, but it has since evolved to become a general purpose, high-level programming language that's used all over the place. The scientific computing community has really taken to Python, has really latched onto Python for reasons that we'll discuss more in later classes. One of the things that's so great about it, it is constantly evolving. It's open source, so it's free. That also means it is being contributed to by people all over the world. So people want to use Python for X, fill in the blank. So they get together with other people in their community, they develop the codes, the softwares within Python, or they link some Fortran code or C++ code or whatever within a Python framework to do it. And it's very, very straightforward in Python. So this is a very exciting time, actually. I am not the type that switches programming languages frequently or easily. I have to be clearly convinced why I should do it and why there's advantages. I started with Fortran because that was the only thing that was available really for numerical programming early in my career. I learned C, but I never used it for numerical programming because it was never better and still is not better than Fortran. I do use Mathematica for certain things. Now I have just fallen in love. It was love at first sight with Python. And we'll discuss that more. And this is common. A lot of people are falling in love with Python. I don't know if Python loves me. First of all, the important thing is this is Python, not Python the snake, but Python as in Monty Python. And it's very important. If you don't know that, then people will laugh at you. So it's Python as in Monty Python, not the snake Python. Dropbox. Do any of you use Dropbox? I use Dropbox every day. Dropbox software, which is actually quite complicated, and that's what makes Dropbox so beautifully simple to use, is all written in Python. So it is really taking over the world, and certainly within the scientific computing community, and I'll describe again later in a later class, more specifically why that is. So I'm going to give you little snippets of discussion about programming. We'll kind of ease our way into the question of everyone's question of, well, what should I use? And I'll just tell you right now, I'm not going to tell you what to use, but I'm going to give you the pros and cons of the different choices. And in the end, I'm going to encourage you to use Python. I'm not requiring you to use Python, but I will encourage you to Python, and I will give you the reasons why. But we'll discuss Matlab, Mathematica, Fortran, C++, and Python in more detail, so you can get a better feel for them. They all have advantages and disadvantages. It's not a clear, obvious choice. Okay, so we're out of time. Any questions that we need to get answered before we go? Any of my Zoomers or in person? All right, so we'll pick this up on Thursday, and we'll look at some milestones in supercomputer development, which is kind of fun and interesting to look at. So we'll continue this introduction, and then we'll get into a review, a fairly quick and abbreviated review of linear algebra. We don't need to know a lot, but it'll make our lives a whole lot easier. All right, so I'll see you on Thursday.